Okay, welcome to this short video where I will show you how to do a simple calculation of wave-runup using a tool that I prepared. So the tool is available from my GitHub repository. Coastal Hydrodynamics is the name of the repo, and you can go inside here. There's a bunch of different coastal hydrodynamics tools. This is the very first one I did, and the other ones will appear here. So you can go on wave-runup model, and here you have a bunch of text describing you what we are going to do via this repository. So inside this repo, there are already wave and tide data, which we will need, and IPCC AR6 sea level scenarios, which we will also need to calculate potential run-up under future sea level conditions. I'm going to explain this all to you while we go through the tools. This is designed to work in Google Colaboratory, which is an interface set up by Google, so you can basically use Python without having to install anything. So what you will have to do is download this repository, wave-runup model, and load it in your Google Drive. I already did it here, so this is how it's going to look like once you have uploaded everything. As you see, you have two CSV files, which is the wave buoy tide gauge data, and you have here the IPCC AR6 sea level projections, which I will show you how to download. And then you have this calculate wave run-up notebook. This is a Google Colaboratory notebook, and if you are in Google Colab, you just double click on it and it will open up in Google Colab. Good. So this is ready to be used, ready to go. If you don't have Google Colab installed in your Google environment, it's very simple. You just it will just require you ask you to install Google Colab and accessing Google Colaboratory, and this is what you will see after accepting a few things. So the first thing we need to do is to get started here. First of all, you change this to the folder in your Google Drive where you put your data. In my case, I call this runup/runup calculations, but you can choose whatever you like. And the first thing you do is to basically run this cell. You run the cells via this little play button up here. And it's already done for me, but actually the first time around we do something like this. So the first time around, sorry, I forgot, we have to uncomment this, which is basically downloading some tools that we're gonna need later on. So let me rerun it again, and it's going to clone py-wave-runup, and it will download it. Now if you go back to your Google Drive folder, you will have something downloaded here, which is the scripts we need from another repository to work with wave-runup. After we did this, we need to import a few libraries, nothing special. We have pandas, matplotlib, numpy, seaborn, a couple of widgets, and then we also imported the py-wave-runup, which is the one we just loaded. So it's gonna take a second, and this is it. Next one, I told you that we already have preloaded wave and tide data. So we identify them here and we load them up into the system using pandas. So this is the tide data, and you have a sample of the tide data here. If you have your own tide data, make sure you follow the same format of the file that you have as an example, and also the wave data. There you go. So we imported the wave data here. So next thing we do is to visualize the wave and tide data over time. So basically we run this cell, and this cell is going to produce a graph where we show significant wave height, wave period on the same graph over time, and then the water level from the tide gauge. The example I have is from a swell which happened in northern Italy in 2018. And this was one of the most destructive storms in the last 30-40 years. So you see that we have significant wave heights of up to 6 meters, periods of up to 12 seconds, and a bit of a storm surge right when the swell was picking up. So about 0.767 meters of storm surge. This plot is, as you see here, saved in your repository. So if you go now back to your repository, we refresh it just to be sure, you have this, which is the figure that I just showed you on the notebook. Okay. Next thing we do is to merge these data by time. So they have time steps, these two data sets, and we need to put them together. So we will then use in run-up calculations. So this is another cell. Everything is explained here to basically tell you, to basically merge according to the nearest tide data and the nearest in time wave data, merge them together and create a unique data frame. This is the first few lines of that data frame. Next thing we do to calculate run-up, we need to know the beach slope. So we need to know how the beach is basically sloping, and we can do that from field data. For example, we can do that. There are also some techniques from satellite data, and this cell is basically asking you to provide some samples of the beach slope. So you have here a text box, so you have to calculate your beach slopes offline. You will have some different techniques, for example, in QGIS 0.02, so you insert them comma separated, 0.035, 0.025, 0.03, something like this. I can calculate as many as I want from field data, and then I insert them here. So I press enter, and these are taken into account. And what's happening inside here is that it's a random distribution is created by these values. So the more you have, the better it is. And then we sample this random distribution to basically create a distribution of slopes which is meaningful. Next, we go into the calculation of wave run-up. What is wave run-up is explained a little bit here. Wave run-up is basically the maximum vertical extent that the waves reach as they rush up off the beach. So you actually get up on the beach, and the wave run-up is the maximum level reached by the waves. And this is important for engineering purposes. Now, there's many different ways of calculating wave run-up. What we're using here are empirical equations tuned into different areas. So they're not perfect, but they can give you a first idea of wave run-up when you have a certain wave height, a certain wave period, and a certain slope of the beach. You see why the slope of the beach is important here, because the more high the slope is, the less the run-up will be. Okay, so in this step we use the py-wave-runup to calculate the 2% exceedance run-up level for the swell that I showed you. So throughout the swell we calculate wave run-up using the significant wave height that we plotted, the period that we plotted, the beach slope that we gave to the program, and the tide level, because it's important to have the tide level added on top of the run-up, as you see here, because the higher the tide when the wave happens, of course, the higher the run-up will be. So if you're curious about the tool that we're using, you can visit this website. Yes, I want to see it. Okay, this is a py-wave-runup, is a tool done in 2019 by Chris Lehman, and it's actually simplifying lots of different models that are published in literature. Now we use only some of them because others would require implementation of many things. But at least they give you an idea. And if you want to dig into the formulas, here they are. And also, if you want to dig into the papers, here they are. You have all the papers and all the formulas here, so you can actually dig into it. So what we do is we take, you see here, our wave height, our period, our tide, and our slope, and we apply all these different models. Okay. It takes a second because these are very simple mathematical formulas. These are not models per se, but these are just empirical formulas telling you where the run-up will reach with a certain wave height, period, tide, and sea level. And beach slope. And then we basically make a plot of this all. The figure is again saved in the same folder. So you see that different run-up formulas, Stockton, this is one of the most common ones, Woduskas, Holman, Nielsen, Ruggiero, Atkinson, Senechal, and Passarella. They basically give you slightly different run-up values. But, you know, for this swell, we have like, say, an average of 1.5 meters for all of them. Nielsen is a little bit more extreme, but all the others seem to align to the 1.5 meters. And here you have the all models combined. So here you have basically all the models, what they're telling you. You see that some maxima, they can get up to 4 or 5 meters, but the bulk of them is concentrating around this 1 to 2.5 meters, 1 to 2 range, basically. Then we might be interested to know what's going to happen if we raise sea level. I mean, with the sea level rise scenarios. And to do that, we turn to the IPCC sixth assessment report. With that, lots of data came, and especially a projection tool came, which is very, very interesting, where you can basically have, from each tide gauge around the world, the future projections. So in this case, for this experiment, I used the Genoa tide gauge, which is here. The wave buoy data is coming from round about here, this area here. But for example, let's take Venice. That's another place, and I can go to full projection. And of course, I can play out with different scenarios, different emission scenarios for the future. So I can turn on and off different emission scenarios for the future. Let me turn them all. This is the low confidence scenario, which can go very high. But particularly interesting here is that you can get all the data. So you can download all the data for this location here, and it's downloaded here. Let me show you how it is a little bit. We're going to use it. So here is basically some things about the license, citation and acknowledgements. Always acknowledge the sources of this data. And then what's interesting for us is this, which is basically, well, this is the tide gauge ID from the Permanent Service for Mean Sea Level. This is telling us that you have all the processes taken into account, and in every other tab here, you have the different processes separated, but this is something which is not what we want now. We have the confidence in the scenario, and we have the scenario, and for each scenario we have the quantiles, so you know, the bounds on the distribution of future sea level rise. And then we have years from 2020 to 2150. Okay, so this is what we are playing with. Once you have this file for your station, you just put it in your folder. There is already one in the folder, which is the one for Genoa, for the example I'm telling you about, or I'm showing you about, and this is basically already copied in here, but you just copy and paste it in there, and you put the name of that file in here. So this is the name of the file that I just downloaded and put in my Google Drive folder. So again, I load it, and it tells me what scenarios there are in that file that I showed you, what years there are, and what the quantiles, what quantiles there are. This is always the same for each file. Any file you will select as the same scenarios. So we then select the sea level rise scenarios, and this is a bit of an interactive tool. So you click on here, and you select which scenario you want. Let's say I want a mid-range scenario, and I want to know what's going to happen in 2100. I get the projection, and it's telling me that the median, so the 50th percentile, is 0.513 meters. Of course, you know, the lower quantiles will be lower, the higher quantiles will be higher. And then what we do is we use these values, we use the values within this scenario to basically adjust our wave run up. Again, here it's all written. You can read how we did it. So we just go here, and nothing is happening here. It's just calculations happening. But then we plot these run-ups. We plot where the run-up would be according to the sea level, to the new sea level. So here you have the run-up distribution today for all models. This is another kind of visualization. It's a kernel density estimate for that basically shows the same thing you had in the histograms before, just in a kernel way, in a smoothed way, if you want. You have the mean of all models, which is 1.54. And here you have what would happen within the 5th quantile, 17th quantile, 50%, 83%, 95% quantile. So this is basically all the scenarios. So the most likely, if you want, would be the 50th quantile, but then you have a bracket basically between the 5th and the 95th% probability of this happening. Now, there is something very important to say at this point. The thing which is important to say is that we are assuming in this, using this kind of model, that the world is behaving like bathtub. So we just raise the sea level and then we will just have the same run up. But if you think about it, it's a very big approximation, because if you start raising sea level, you might have coastal erosion, you might have different infrastructures working in different ways, you might have several other processes starting to act, the beach slope might change, for example. So this is a very, very rough way to see things, but it can give us an idea, it can give us a little bit of an idea of what could happen. So for example, the sea level, so the run-up, which is today 1.5 meters, more or less, well, it can get up to 2.5 meters on a 95% quantile in the future. Last thing that we do is we just export the data that was used to make this graph and this graph, so you can analyze them in any other software you want. For example, one thing you can do is to take one of these values, or the average of these values, and basically plot it on a map in QGIS as elevation, if you have digital elevation models of the coastal areas. Again, this is a very, very rough way to calculate run-up on one side. We are using empirical equations which were tuned in some places but might not be applicable for other places. It's a very empirical way to also project what will happen in the future, because the run-up conditions, the boundary conditions of the run-up might change as you raise sea level. Engineers tend to steer away, and also practitioners tend to steer away from these very simple models, because there's lots of uncertainty in them, and also because it's basically thinking that the coast will remain exactly the same as you start rising sea level, which is not true, which is an assumption that basically fails if you start really looking at it. But this can give us an idea of what could happen. Again, all the images are saved. The run-up histograms, for example, are saved by year and by scenario. So in case you want to go back, you can also do this. You can select a very, very rough scenario, SPP 5.8, and then rerun these cells. Things will change. Okay, I didn't run it. Okay, things will change here, and basically you see that adopting a higher sea level scenario, also the run-up will start shifting higher. Okay, so this is what it is. And just to show you, once you go into your run-up, into your Google Drive folder, at this point you would have the two different scenarios. So you can actually start making comparison about the scenarios. And of course you have the data for all your scenarios, so you can start making some comparisons about this. I hope this was good. So if you think that there's something better that can be done, you can also leave a comment in our repository, in the main one, in the coastal hydrodynamic repository. If you think that something should be better specified, please don't hesitate to comment this video, and look forward to add more tools to this one.